Okay, so last week we talked about proton and carbon NMR, and we also looked at a little bit of mass spec, and we're going to finish mass spec up today. But what I wanted to do now is have this in-class activity so that we could use for the carbon NMR, and then comparing and contrasting a proton NMR and a carbon NMR to see how you could get more information from each of them. Okay, so what we're going to do here is we're going to start with this system here, and notice the instructions are a little different. We wanted 4 things for proton NMR, right? We wanted number of peaks, the shift of those peaks, the intensity of those peaks, and the peak-peak splitting. Okay, carbon NMR, all we need is shift and number of peaks. So we're going to identify where they are and compare and contrast. So when we did this molecule here with proton NMR, we only had 3 signals. Oh, it's still not there. Display on. There. All right. Sorry. So we had 1 signal here, 1 here, and 1 here for proton NMR, but we have a carbonyl. Don't forget the carbonyl when you talk about carbon NMR. So we have A, B, C, and D. Okay. Of A, B, C, and D, where is going to be the one that's going to be furthest downfield, highest number? Going to be B, right? Because it's a carbonyl, and so that carbonyl in ketones and aldehydes like this is going to be way up next 200. So we're going to do 200, and we're going to have a peak there. And way down here is going to be 0 right here. Okay, so A is going to be up here at 200. I'm sorry, B is going to be up here at 200. All right, now let's look at C and A. Okay, they're going to be our next most downfield because they are 1 bond away from the carbonyl. So we're going to have there, and that A and C, which one's going to be further downfield? Probably going to be A, because the other one has a donatable, has a carbon on the other side to help donate, but they're going to be right together. So A and C are going to be right here, 2 more signals. And then where's D going to be? Right, it's almost to like a hydrocarbon at that point. So it's going to be below 20, maybe 15, and be D here. So we know how many signals we want to see, and we know their approximate location. We're going to have these going to be around, 50. If there was an oxygen attached to it, that would be push them up around 70. If we had a double bond, that would get them up to 120. Benzene rings up to 150. And then so we'll watch that, all those move. Okay, questions on this one? Can't see me. Oh, there we go. Hi. All right. My camera light went on. I mean, my little slider. Okay. All right, so now let's predict this one. Remember, we had 5 signals in proton NMR, but we only have 4 signals in the carbon NMR. We have A, B, C, and D. Okay. Obviously, oxygen doesn't show up on proton NMR. But which of these peaks is going to be most downfield? B, because it's directly attached to the oxygen. And so it's going to be, somewhere around 70. So I'm going to put a 70 right here because it's going to be our furthest downfield. And I'm going to do a 0 over here. And so I'm going to put B. It's right here. And then what would be next? A and C, because they're 1 bond away. So A and C are going to be a little further back, and that's going to be A and C right here. And that puts D way down here, close to 10 again. Okay, so we're seeing how those, so the reason I do this is that if you can predict where they should be, then you should be able to say, oh, look at where the peaks are, and say, I predicted they would be here, here, and here, and are they or are they not? Yes. Because it has 3 hydrogens and no donating carbon. The carbon actually can donate a little electron density to shift it just a little bit. Okay, so now let's do this one. Okay, we're going to have A, B, C, and D. So which one's going to be the furthest downfield? Well, D and C are going to be about in the same place, right? And they're going to be further downfield than the ones next to the bromine. So we're going to have C and D up here around 70 again. So we have those there. And then where's A going to fall next?
I have a question.
Yeah.
So
Yeah.
with the C and D, why wouldn't it be like with the example above that the C isn't like sharing it with the D?
Oh, yeah, that you're right. I need to do it D and C.
Okay, so it is.
Yeah. Sorry. So what's going to be next? Well, we have bromine, and bromine doesn't pull as much as oxygen does, and it's because, you know, nuclear electrophilicity goes down as you go down a row here. So I think that we're going to have the next one's going to be around 50, and that's going to be A. It's going to be right around 50, and then B is going to be our last one. But it's also not going to be as low as the methyl groups that we have over here. This is going to be down like around 10 or 15. This is probably, B is probably going to be closer to 20 to 25 because it's got this one with electron withdrawing group, this one with electron withdrawing group, and so it's going to pull it. So it's not going to be as far down as here because this is so many bonds away from an electron-rich atom. All right, so let's do this last one. So we have 6 peaks, right? No, we have symmetry again, okay? So in this case here, I think we're gonna have these two right here are gonna be the same. Carbonyls, they're ketones, so they're probably gonna be down next to 200, maybe a little above. And then we have, this is a unique carbon. It's the only one that has 2 carbonyls bonding to it, so it's a unique carbon. We have these two that are the same, because if you follow around the circle, they're both the same now. And that leaves our last one right here as a peak. So we have 4 peaks, okay? And our carbonyls are going to be the furthest downfield. So I'm going to label, let's go A, B, C, and D. So C is going to be down near 200. 200. And then the next thing that's going to be there, which is next, D or B? D, because it has 2 carbonyls pulling on it. Okay, so it has 2 carbonyls pulling on it. So that's going to be closer to, you know, like 40 or 50. We're going to have D. And then we're going to have B. And then we're going to have A way down here around 10 or 15. 25. Okay. So see how you can construct what you should be seeing in your spectrum. Okay. All right. So now let's try it the other way around. Let's look at a spectrum and see what happens. All right. So we don't have to worry about splitting. All we have to worry about is number of signals. And so we have 1 signal, 2 signals, 3 signals, 4 signals, 5 signals. So we're looking for something with 5 signals. But what's special about those signals? Okay. This is 150, this is 100, and this is 200. So what does that tell us about this farthest downfield peak? Tells us it's a carbonyl, but it's not an aldehyde or a ketone. It's got some on the electronegative atom on it. So that means we have a carbonyl with either an oxygen or a nitrogen or a chlorine or a halogen. Okay. So, and then we have these that all look pretty close to just being regular carbons. Okay. So now let's look at our choices. Okay. So we have an aldehyde, a ketone, and a ketone. So we can immediately eliminate all those. But does it match? Okay, we have 1, 2, 3, 4 that are almost just normal hydrocarbons. So they're down here. We got 4 peaks down there. That's good. And we have a carbonyl peak, and we have a carbonyl with an oxygen, a nitrogen, or a sulfur, or a chlorine on it. So that means that we do have correct number of peaks in the correct ranges. Does that make sense? Okay. So even if you didn't know, if you knew that aldehydes and ketones were going to be above 185, you can immediately eliminate them from one of your choices. Yeah.
That little like tiny peak that kind of is like.
That?
Yeah.
That's the solvent.
Okay.
That's the solvent. It's chloroform. It's 3 peaks and it's right at 77. Usually, I wouldn't want you to think that that's a peak. It's just, there'll be little teeny tiny things of impurities here and there, but this happens to be the solvent.
Okay.
So see, it shows up here too. But then there's this little impurity down here that we don't care about, and that's the solvent.
Just the big peaks.
Yeah. So here we have, let's see, we have something above 150, something above 100. So what's the thing between 100 and 150? It's got to be a double bond, right? Because it's got to be something that has that in it. Okay. And again, our 150 to 200, that has to be a carbonyl with an oxygen, nitrogen, or a halogen on it. And then we have 1, 2. Okay, so we have 1, 2, 3, 4 peaks, and only 4 peaks. So let's look at our choices and see what we have here. Okay, so right away, I'm going to say the one on the far right can't be our material. Why? It doesn't have the double bond. So that can be eliminated. So the other 3 have double bonds, so that's cool. Can we eliminate anything else just right now and just by the peaks we know? Can we eliminate the one on the far left? They're ketones. They're not esters or, yeah. So we can't have that one because it's ketones. All right, now let's do the last 2. Let's see, we're going to have 1 signal here, 1 signal here, and 1 signal here. And then it's symmetrical. So this is going to have 3 signals. Okay. Let's see, 1 signal here, 1 signal here, 1 signal here, 1 signal here. This is going to have 4 signals. So which one is it? It's the one with 4 signals because we have 4 peaks on our spectrum. Okay. So that's how to attack these NMR problems. That's why the prediction really helps, because you can see where it's supposed to be. And right here, we got to eliminate 2 things because of shift. Then we got to eliminate 1 more because of number of peaks. Okay, so try to do one or the other and both, and if they agree. And let's think about this. This peak right here is going to be this one. This peak is going to be this down one here. The alkene is going to be this one, and the carbonyl is going to be the highest one. So it fits. All the pieces fit together correctly. Okay. All right. Now let's do the other one. This is the other sheet you have. So what I want you to do is we're going to take information from the proton NMR and information from the carbon NMR and put them together to solve our problem here. Okay, so the first thing we have, let's look at the proton NMR first. Okay, so we have this weird peak here. What's that? Only 1 peak is not really narrow in proton NMR. It's an alcohol. It's something that hydrogen bonds. If it hydrogen bonds, it does a broad peak. So this has got to be an OH. Let's see. This seems to be, looks like a quartet. So there's 4 peaks here. And this is something bonded next to an oxygen. Probably something like that. This is a lot of peaks. wow, that's a lot of peaks. I'm going to say it's 5, 7, or 9. Don't know. And then this one is 2 peaks. Okay. So we have 1, 2, 3, 4 kinds of hydrogen. Okay. So now let's look at the carbon NMR. Okay, carbon NMR is a little bit cleaner. We have no carbonyls. We have no double bonds. We have something bonded to an oxygen. And then we have 2 other things. So we only have 3 signals for carbon. Okay, 4 signals for hydrogen, 3 signals for carbon. Okay, let's look at our choices. Okay, can we eliminate the one on the left? Because it doesn't have an OH. So we can eliminate that one. And we can eliminate this one because there's no carbonyl in our system. So it's got to be one of these. Okay. So now let's figure out how many proton signals that each would have. Let's see, we're going to have 1 here, 2 here. These hydrogens are going to be 3, and then these hydrogens are going to be 4. So let me circle that. These hydrogens are going to give 1 signal. These hydrogens are going to give 1 signal. This hydrogen is going to give 1 signal, and that one's going to give 1 signal. Okay, so that didn't help. Let's go over here. Let's see, we have these 2 methyl groups are going to give 1 signal. This hydrogen is going to give 1 signal. These 2 hydrogens are going to give 1 signal, and then that's going to get, oh, rats. 4 signals again. Okay, let's look at the carbon and see if we can't decipher it from the carbon. Let's see, how many signals for carbon are we going to get on this one? We're going to get 1, 2, 3. Okay, let's see about this one over here. How many signals for carbon we're going to get? We're going to get 1 for those 2, 2 and 3. Oh, darn it. So we didn't do it the easy way. I guess we're going to have to do splitting. Okay, so let's figure out what our splitting patterns would be. And let's see. Remember, we don't split through oxygen. So that means that these 2 protons here are only next to 1 proton. So our N is 1. So N plus 1 is equal to 2. So that would be a doublet right there. Now these right here, those 2 methyl groups are only next to 1 hydrogen right here. So that means those are going to be split into a doublet. And then this one right here is going to have what? We have 3 there, we have 6, 7, 8. So our N is 8. So that means we're going to be split a 9. So it's going to be 2, 9, 2. Okay. Oh, wait a minute. We're going to have more hydrogen signals on this, right? What about when we do this? We're going to have OH up here with an H here. And then these hydrogens up here are going to be different than the hydrogens down below. And then these hydrogens are probably going to be all the same because they're far enough away. So these hydrogens are actually going to be different than the hydrogens down below, those hydrogens down below. So we're actually going to have 1 signal, 2 signals, 3 signals, 4 signals, and 5 signals. We have 3 signals in proton. So that means it can't be this one. It can't be this one. So it has to be this one right here. Well, it does look like that's split by, could be 4 or it looks like 4, but it is 2, possibly 9, and then 2. So it has to be that one because of the splitting. Okay, so see how you can use a little bit of information from one, a little bit of information from the other, and come to a good decision.
The reason why I can't do it for this right one is because the orientation so
the far right one, the cyclic one, is because we would have had an extra signal. We would have had one more signal in the proton NMR. because I count 5 signals on that. Once you put the ring on its side, and so where the OH is on above and the hydrogens down below, the 2 hydrogens that are in through space to those are going to be giving a different signal. The 2 on top. Okay. All right. So let's look at this one right here. It looks like we got maybe 4, a 3, and a 1. Okay. So wait a minute. We had one of those cool patterns that we always could see. It was 4 and 3, right? If you have an ethyl group, CH2, CH3, this is going to be split into 4, and this is going to be split into 3. So we might have an ethyl group in our system. And then we have something that doesn't have anything. And this one right here is definitely bound next to an oxygen because it's up in 4. This one's further away. But hey, wait, this one up here too. What's it probably next to? I think it might be a ketone where it's a methyl group on a ketone, because then there's no way to split. Okay, but hey, let's see what the carbon tells us. Maybe the carbon will help us say that it's a ketone. Okay, so, well, we have a peak way up here, but it's not above, 185. So that means we have a carbonyl with an oxygen on it here. And we have 1, 2, 3, 4 peaks. So let's see. Can it be this one right here? Can it be the carboxylic acid? No. Even though it fits the carbon NMR, we have 1 too many carbon peaks here. The carbonyl, 1, 2, 3, 4. That would give us 5 peaks. And we didn't see the OH in the proton NMR. So it can't be that one, okay? So we know we have an oxygen bound to our carbonyl. So that is not that one, because that one would be up here. So it's got to be one of these. Okay, so how do we know? Well, let's go back to our proton, because in our proton, we had signals that had a 4 splitting and a 3 splitting, so they have to be together, right? So we're looking for something that is a methyl group all by itself on the other side of the carbonyl. So let's look at our choices again. Right here, we have an ethyl group and this one. Okay, but that wouldn't give us the right peak. It's got to be this one right here, because these 4 protons are shifted further downfield than these 3 protons that aren't split. So it has to be this one. It can't be this one, because this would be a singlet the farthest down near 4, and then the quartet and the triplet would be lower, closer in field. So that means we can choose that as our final product. All right, questions on that? Okay, so do you see how to attack these NMR problems now? You want to attack the NMR problem with, okay, how many signals? What's the splitting? Does my proton and my carbon agree? And so when I ask these questions, it's it's going to be one of them is going to be the correct answer, and the others are not going to be right because of something like this. These look like the same compound. These 2 in the middle look like the same compound, but they're going to have different shifts. So we've solved by shift. We knew it had to have an ethyl group because of splitting. So the ethyl group had to be there. So that means it couldn't be this because the splitting wasn't there. We had too many signals. And it couldn't be this because the shift wasn't there. So we got down to these 2 because of shift, and we got down to this one because of the spin-spin coupling. Okay. All right. So quiz will be on chapter 9 only on Wednesday. 9 only. Okay. So what I want to do now is I want to finish up with, I got to go to the other class. I want to finish up with our, not that, this one. All right. And so we were all the way down to our mass spec. Okay. So let's refresh our memory what mass spec was. We have something that we are going to ionize, and we have 4 things we're looking for in a mass spec. The molecular ion peak, the highest peak. 2, The base peak, I'm sorry, molecular ion peak is the highest molecular weight peak. Okay. Base peak is the tallest peak, and that's taken to 0. So everything else is a percentage of that base peak, right? And then fragmentation and relative abundance. Look for those fragments like, oh, something that weighed 35 fell off. Or if a 15 fell off, that's a methyl group, a CH3 group. If a 17 falls off, that's an OH. Looking for those fragments that fall off. Okay. Okay. So we are not determining, oh, that's why I have new slides. Sorry, they're shorter slides. And we're not going to do the calculating molecular weight thing. We did that, and there. All right, so now let's talk about isotopes, okay? So in the case of looking at that spectrum, remember I said that carbon had that little teeny peak on it. It was 1.1% of the other peak, and it was a mass plus 1, okay? So where that comes from is the fact that carbon 12 is the most common isotope, but there's 1.1% of the carbon 13, and that's where it shows up. It helps us in carbon NMR, but it also helps us in our mass spec here. Hydrogen also has isotopes, but the isotope is very small. We hardly ever see it in mass spec, okay? Nitrogen has a little bit right here. Oxygen has some, you occasionally see this, but notice that's oxygen 18. So oxygen 16, and so that's an M plus 2, the molecular weight of the parent element, that isotope, and it's plus 2. Okay, so you can see it from time to time. Fluorine actually only has the one isomer at 19. Silicon actually has 2 isomers. One's an M plus 1 for 29, one's an M plus 2 for 30, okay? But look at the amounts, 5% and 3%. So you're gonna see your silicon is gonna have this huge peak, and then it's gonna have a 5 and 3 right next to it. One's gonna be plus 1, one's gonna be plus 2, okay? Phosphorus only has the 1, sulfur has a small amount of this, but look at this. This M plus 2 shows up, it's almost 5%, it's 4.4%. So you might see that in the thing. But now here's the 3 things that are the most illuminating here. Right here. We have chlorine has an M and an M plus 2. And notice that M plus 2 is 32%. So that means when you have chlorine in your system, you're going to have your M peak and an M plus 2 peak that's going to be 1/3 that height, or about 1/3, yeah. But look what bromine does. You have 79 and 81, so you have an M plus 2 peak, but they're 50-50. You're going to see them, they're just going to stand right together, and there's going to be very obvious, okay? So that is one of the cool things about these. So that means when we look for those isotopes, we can see them in our system. So like I said before, if we take our intensity of this peak right here and compared it with this, that would be 1.1% of that 72 peak. So we can see the isotope. We can see the isotope. Okay, and then you can calculate that out if you want to. Now let's look at an M plus 2. In the case of the bromine and the chlorine, they have very distinct patterns. Okay, and I'm going to pull the chlorine up first. So if we look at that, we have our M peak, which is this right here, and then we have our M plus 2. So this is our 35 isotope. This is our 37 isotope. And notice it's about 1/3 the height of there. That pattern will be consistent. If you ever see this pattern in a quiz question, exam question, you can say, yeah, which halogen is on this compound? And you'll say, oh, because of the M plus 2 isotope effect, it has to be chlorine. Okay. So what does bromine look like? Well, bromine is a little different because they are the same height. They're almost exactly the same height, but it's an M plus 2 peak. So this is our M. This is our M, and then this is our M+2. All right, let's talk a little bit about fragmentation. Okay. Notice the bromine falls off this one first. How do we know that? There's two ways to know it. First way is you lose 79 as a mass. So that means that that bromine just fell off. And there. The other thing we can say is we don't have a peak down here that has that same two heights. None of those peaks are the same height, and therefore the bromine had to fall off as well. So in this case, the fragmentation pattern shows bromine breaking off and leaving this stable fragment, this 43 fragment left. Let's look at what happens when you have this in the chlorine. We have our M and our M+2, but look at this. We have, this has the exact same pattern as that. What does that mean? That means the chlorine didn't fall off first. It means we lost a methyl group first. Then to get here, it had to lose the chlorine. So there's at least one fragment here that has the chlorine still on it because it has the same isotope pattern for chlorine. All right, questions on that? Okay. So there's another cool thing about isotopes, and it's the nitrogen rule. If your mass spec has an even number, notice 43, 73, 1, all of them were odd. All of them, the peaks were odd. If your mass spec has a even parent ion peak or the molecular ion peak, that means you have to have, odd, yeah. If you have an odd molecular ion peak, that means you have an odd number of nitrogens, 1, 3, 5, or 7. Now, if you have an even number of nitrogens, it actually gives you an even peak. So look here on this one right here, the lower one, we have only one nitrogen, and it's giving us an odd parent ion peak. Not the fragment peak, it's the odd parent ion peak. Look at what we did over here. So we had even parent ion peaks right here because there's no nitrogen in them. We have an even molecular ion peak, no nitrogen in it. And all of these had even. So we're looking at, that's the difference there. So if you have an odd molecular ion peak, you can say your compound has nitrogen in it. 1, 3, or 5, an odd number of nitrogens. So that's a really good way to distinguish between two choices that you're given, saying, oh, molecular ion peaks odd. So that means it has to be the whatever choice you have with a nitrogen in, one nitrogen in. All right. So the last thing I want to talk about is how we can actually use this, okay? If you have a pure compound, you can just use mass spec, okay? Because it's going to fragment and it's going to give you one peak right there. But what if you have a mixture? Well, if you have a mixture, you have to separate out the components. And the easiest way to do that is using gas chromatography. So in gas chromatography, you'd put your mixture of your sample into the injector, and then they are going to be separated by boiling point. So the lowest boiling thing is going to come out first. It's going to go into the ion source, and it's going to be jolted into a radical cation, and then that's going to decompose into a radical and a cation. Now remember, we only see the cations. And the reason we only see the cations is that cation is going to start flying through here, and then there's going to be magnetic bars on either side here that are going to control how fast it goes and focus it in on the detector. And then when the detector feels it, it gives a mass, okay? So then when the next piece comes through, it gets ionized, and then it has a single peak. And so you'll have one peak for the chromatogram and for the thing, the boiling point difference there. And then you'll have a molecular, you'll have that molecular ion peak for that. And so you can tell, oh, this one's 72, this one's 85. So that means my first one is this compound, my second one is this compound. So that's another great way to use mass spectrometry to help us. Okay, questions on that? Okay, that's the end of chapter 9. And so our quiz will be on chapter 9 on Wednesday. But let's go ahead and start chapter 10, radical reactions. Okay, before I start, let's go ahead and take roll. All right. Okay, so up to now, we've been following pairs of electrons around, right? 2 electrons are in the pi bond, 2 electrons in a sigma bond. 2 electrons in your nucleophile reach out and make a new sigma bond. We're using 2 electrons. Well, now we're going to talk something a little different. We're going to talk about a different kind of bond cleavage. So up to now, we've been doing what we call heterolytic cleavage, meaning that the 2 components walk away with something else. And always the one with the more electronegative one is the one that walks away with the electrons. Okay. In this case, what if you have 2 things that have the exact same electronegativity? Which one's going to walk away with a positive charge? Well, neither one. So what they're going to do is we're going to do what we call homolytic bond cleavage. They're going to walk away with the same number of electrons. Okay. And in that case, we have an unpaired, I'm sorry, I thought I knew that already. We have an unpaired electron. So unpaired electrons are very, very reactive. Now, let's look at our arrows here. Notice we have 2 barbs on our arrow when we have heterolytic cleavage. That's because both of those electrons are moving with it. So 2 barbs means 2 electrons. 1 barb means 1 electron. Okay. So when you see it, look very carefully at that. You can tell whether it's a radical reaction because of the barbed arrows. Okay. So what we'll see here is those radicals, once they form, are what we call free radicals, or the very reactive species. And they have a lot of different reactions involve radicals and radical anions and radical cations and stuff like that. Because all you have to do is transfer, you get that 1 electron, and they are very reactive. Okay, so what can a radical do? A radical can do 2 things. A radical can do hydrogen abstraction, which is pulling a hydrogen off a hydrocarbon and then leaving a carbon radical. Okay, and so what that would look like is this first one right here. We're going to break a sigma bond, usually between hydrogen and carbon. One of the electrons is going to go to the carbon. One of the electrons is going to be used to make the new sigma bond with whatever the radical was. So this is radical abstraction, breaking a hydrocarbon bond. Okay, and it generated a radical. In fact, what you're going to notice is most reactions, when you have a radical attacking a neutral species, it'll create a radical. So that's how we're creating that radical on the carbon. Okay. Now, the other thing we can do is we can add to a double bond. But again, we're only having 1 electron here. So the 1 electron comes in, so only 1 electron of the double bond is going to be used to form that sigma bond. And the other one is going to reside on the carbon, giving us another radical. So radicals give us radicals. Okay. And so they either abstract a hydrogen to get a radical on a carbon, or they add across the double bond to get a radical on the other carbon that wasn't added to. Okay. So that's cool that there's only 2 kind of things that that they can do. So let's talk about stability. Okay. In the case of radical stability, it trends with carbocation stability. Now, think about that. In a carbocation, we have an sp2 hybridized carbon with an unhybridized p orbital with 0 electrons in it. That's a carbocation. In a radical, we have an sp2 hybridized orbital with a p unhybridized p with 1 electron in it. So it can be in the top or the bottom. In fact, it's half the time at the top, half the time at the bottom. Okay. So in the case here, it's going to trend with carbocation stability, making tertiaries more stable than secondaries, which are more stable than primaries and methyl groups. Okay. But unlike carbocations, the difference in energy is not as great. So we can make a primary radical, we can make a methyl radical in regular conditions. And still the tertiary and the secondary are going to be more stable, but we can make them. They're not that big a difference. Okay. So it's important to think about, now we have this structure here. So that means that we're going to have some stereochemistry issues associated with that, meaning we're going to racemize our stereochemistry if we have stereochemistry. Okay, so what's the driving force for this? Okay, we use this driving force is to, of course, make a more stable product. Okay, so in the case of this example here, we're going to take two equivalents of hydrogen and two equivalents of fluorine, break them apart, and reform a new compound HF. Okay, so in the case of this, we can, the energy it takes to break a hydrogen-hydrogen bond to give us two radicals is 436 kilojoules per mole. Okay, to break apart two of the fluorines, it doesn't take as much. Okay, it's 195 kilojoules per mole. Why would it be less energy? Longer bond, really electrophilic, really wants the electrons, so it's a longer bond. And then if we reacted those sets of fluorines, it would actually give us 570 kilojoules per mole for each of these reacting. So that's a total of 1146 kilojoules per mole. Now, whenever we have this, we want to take the total energy change in your reaction is the sum of all of your reactants minus all of your products. And if your number is negative, that means it's releasing heat. It means it's an exothermic reaction and the reaction will be spontaneous and move forward. Okay, so let's look at this one right here. We have 436 from the hydrogen, we have 159 from the fluorine, and then we have to subtract both equivalents of the HF, which is this 1400, which gives us a negative 554. Okay. So a negative 554, meaning it's an exothermic reaction, and it wants to move from the hydrogen and fluorine to the hydrogen fluoride acid. Okay. Now, I said that there is not as big a difference in the energies between primaries, secondaries, and tertiary radicals. Okay. Now, here's an example of that. If you have this, this is creating a primary radical at 438 kilojoules per mole. Kilojoules per mole. A secondary radical is only 10 kilojoules per mole more stable. So going from a primary to a secondary is only 10 kilojoules per mole. Going from a secondary to a tertiary is only 10 kilojoules per mole. So there's not much difference. Carbocations, it's like 100. That's why we can't make those primary and methyl carbocations without using your mass spectrometer. Okay, so there are some common features that are in all radical reactions. Remember, a radical reaction only does two things. It can abstract a hydrogen or it can add across a double bond. Okay, so we have to get that reaction started somehow. Okay, so the easiest way to get this started is what we call an initiator. An initiator is something with a weak bond that'll give us two radicals. And one of the most common ones is peroxides or an oxygen-oxygen bond. They're both electrophilic, and so they both want to break apart with the equal number of electrons, so they break into two radicals. Okay, then these radicals then go on to do the hydrogen abstraction to get it on the carbon, so the carbon can then do stuff. So the initiation step is the one that creates the radicals, and it's usually something like peroxide or peralcohol or carboxylic acid. The next one is the propagation step. That's where the radical, the free radical, is starting to react with those they're either extracting hydrogens from hydrocarbons or they're adding across the double bond. And then every time they do that, they generate another radical. So it just keeps going and going and going until you run out of material. Then when you run out of material, you do what we call a termination step. Okay, termination steps can happen when any two radicals form to make a sigma bond, or any two radicals that can cancel each other out and make a sigma bond. That is a termination step. Okay, but some termination steps are productive and some are not. So let's look at that in a little more detail and look at the halogenation for methane using chlorine, and this works for bromine too. Okay, so methane is, I said they don't do much. Hydrocarbons don't do much. So to functionalize them, we're going to use radical chemistry and do that radical hydrogen abstraction so we can put a chlorine on that hydrocarbon. That's how we get our alkyl chlorides. okay? So in this case here, we're going to start with our first step. And so in this case, we're going to use the chlorine as the initiator, okay? Why can we do that? It's two atoms of the same electronegativity. So the breaking it apart to give you your radical is not a bad way to go. You don't want to have a cation chloride and an anion chloride. You want those two radicals. So then that radical does one of the things that it can do, which is hydrogen abstraction, and it creates HCl and generates a methyl radical. So now this methyl radical can go and react with another equivalent of chlorine to give that new chlorine bond and a radical. And then that radical is going to go around, and that radical is going to go up here and do that again. And so it's just going to keep going and going and going until you run out of chlorine or you run out of hydrogens to extract. Then we go for our termination steps. Two chlorines combine to form chlorine gas. Is that a productive step? No, but it's not bad because we use chlorine to begin with. So we're just making starting material so it can go back and continue to be used. We can just use it back up here and let it go. We can do this step right here where we have a chlorine radical is going to react with a methyl radical to create a sigma bond. But hey, that's not bad because that creates product too. Okay. The bad one is when you have a methyl radical attack a methyl radical and it leads to a carbon-carbon bond formation. That is now an impurity and is not one of the products you wanted. You wanted the methyl chloride and you now have ethane. So there can be productive, which means they give you products or can be reused, or non-productive parts of the mechanism. All right, questions on that? Yes.
So to start the initiation step, you just need heat, essentially?
Heat or light. Heat or light. That's what the H nu means. H nu means light and the delta means heat. So yeah, depending on how strong the bond is, like some peroxides start at 50 degrees C, some of them don't start till 100 degrees C. So you actually can choose your reaction temperature by choosing your radical generator, your initiator. So this only works for chlorine and bromine. It doesn't work for iodine or fluorine. Fluorine's too reactive and iodine's actually endothermic. So that doesn't react go. So this is good for chlorine and bromine. All right, so now let's figure out what kind of products we're going to get out of this. Okay, so if we look at this, and we look at this right here on these two methyl groups at the end are basically the same, right? It's butane, they're basically the same. So that we have a total of 6, 3 on one side and 3 on the other, of this type of hydrogen. Okay, now we have, and so those would be the 6 primary hydrogens. Oops. Let me call those primary hydrogens. Primary hydrogens. Okay, and we have 1, 2, 3, 4 secondary hydrogens. 4 secondary hydrogens. Okay, so statistically, you're going to get, let's see, there's 6 more. I mean, there's more than that. So statistically, you should get more of the primary and less of the secondary because of you have a total of 10 hydrogens. So if you reacted 10 of them, 60% should be the ones on the end because there's more of those hydrogens, and 40% should be the ones in the middle because there's less of them. So statistically, but if we look at that, we actually expected a 60-40 split, but we don't get that. We get a 29-71. Okay, something must be wrong here. Okay, maybe it's that stability of the carbocation, or maybe there's something about those different reactions. Maybe a primary radical hydrogen abstraction is faster or slower than a secondary secondary radical hydrogen abstraction. Okay, so as it turns out, by measuring the reaction, we found out that in chlorination, if you have a primary, it's going to be reacting the slowest. For every 1 primary that reacts, 3.8 of the secondaries are going to react. And for every secondary there, your tertiary is going to be even faster. It's 5 to 1, 3 to N1. So because of this is what we call a reactivity ratio for chlorination. Okay, so in that case, how can we use that to predict this experimental result we saw? Okay, well, let's think about that. If we have 6 hydrogens of the primary, right, and its reactivity is 1, we're going to have 6 times 1. So let's say in 10 seconds of the reaction, we've had 6 of the primaries react. Okay, so let's look at the secondaries. We had 4 secondary hydrogens, but it's times 3.8. So it's 3.8 times faster. So that means in that same 10 seconds, even though there were only 4 available, 15 of them reacted in that same 10 seconds. So because it's faster, you got more of that product. Okay, but how do we get those percentages? Well, there's a total of 6 plus 15 equals 21 reactions happened in that 10 seconds. So if we divide 6 by 21, we get, and multiply by 100 to get a percentage, we get 29%. If we might do the 15 by the total number of molecules created, we get 71. Okay, so that's cool, right? Multiply the number of hydrogens available of that type and by its reactivity ratio, and then add up the total number of molecules that are made in that time, and you get the percentages. In fact, it's the exact percentages we see. 29 and 71. In fact, these reactivity ratios are not theoretical, they are measured. Okay, you know how like heats of hydrogen are measured, showing stability? These are measured. Okay, so that's chlorine. That's pretty cool. We can get, some selectivity, but it's going to be a mixture of products, a little 2-chloro and some 1-chloro. What about bromine? Okay, turns out bromine selectivity is a little bit different. Bromine's a little bit softer, can wait around a little while longer, less reactive. So if we took the primary as 1, a secondary would be 82. So for every 1 primary hydrogen abstraction you got 82 secondaries in that same amount of time. And look at that tertiary. For every 1 primary substitution, you have 1,600 tertiary substitutions. So, oh my gosh, that must be really, really selective, right? Because it really, if there's a tertiary that we use. So that means our product ratio is actually different when we use bromine. Our product ratio is not a 29:71 like it was with chlorine, because our reactivity ratios are so much bigger, it actually comes out to 2 to 89. 89% the secondary product. Okay, we only got 71% of the secondary product in chlorine, okay? So that means that bromination is more selective than chlorination. And the chlorination is really exothermic, so that makes all the positions attackable. The bromination is endothermic, which makes some more selective than others. Now, iodine is so endothermic, the reaction doesn't go. But we can add a little bit of energy to the system. See, we're heating it up, and we're adding light. And even though it's an endothermic process, we're adding enough energy to get it to go to products. Okay, so what does that mean? Well, that means that the greater reactivity of your species, the less selective it is. Imagine, it's like the frantic chloride running around going, I gotta react, ah. And then the bromine's just gonna roll in and say, yeah, well, hit me with some light, I'll do my thing. It's fine. Okay. So that means that bromine's more selective. It can wait around and say, hey, I'm just gonna wait for that secondary. I'll just not play with it. But you can use the chlorination to your advantage if you have a symmetrical molecule. Okay, in the case of cyclohexane here, we only have one kind of hydrogen. They're secondary hydrogens. So they're going to react a little bit faster anyway, but now because of symmetry here, that's a useful reaction. We don't have a mixture of products. We have one product. So we're using our smarts to use the high reactivity, but still get one product by using that symmetry. And then fluorine is really way too exothermic to use. Violent explosion, imagine that. A violent explosion. Better than anything in Star Wars. And iodine's just too endothermic, just can't go. So this kind of halogenation takes place only with bromine and chlorine. And bromine is so much more selective than chlorine that works. All right, so that's one thing we can do with radicals. Okay, so radicals can only do a hydrogen abstraction and add across a double bond, okay? When we added HBr to our alkene, and we just used HBr, we didn't have any radical generators, what kind of product do we get? We got the Markovnikov products. The hydrogen was always going to go on the more hydrogenated side or the less substituted side, the less. However, if we add peroxide as our initiating agent, we can make the reaction go backwards. Okay. So technically, you would say that the addition from HBr without peroxides goes Markovnikov addition. But let's say you wanted the secondary bromide. You wanted it, so you now have to do that same reaction, but in the presence of peroxides to go anti, to go opposite there. Okay, so this only works with HBr and HCl. But how does it work? Okay, well, we have 3 steps in any radical reaction. We have initiation, propagation, and termination. So let's look at those. Okay, so we're going to initiate with our peroxide because we want to generate our radical. Why don't we just hit HBr with light? They have 2 different electronegativities. They'll probably spur apart with a hydrogen going as a positive and the bromine going as a negative. Okay, so it won't work. So we have to have that initiator. So we're going to use this initiator, and then the next thing that's going to happen is our initiator is going to abstract the hydrogen from HBr, giving us the bromide radical, bromine radical. Okay, so again, we only do 2 things: add across the double bond and abstract hydrogen. So we've abstracted hydrogen. So now we get to add across the double bond. Okay, so now our radical is going to come and attack with 1 electron. It's the outer, the least substituted carbon, and generate a more stable radical, a secondary carbon radical, more stable than the primary. Okay, now what we have can happen then is this radical that can then abstract a hydrogen from HBr, generating more bromine radical. And so this is our propagation step, keeps going around. But what are our termination steps? Termination steps include bromine-bromine coupling. Okay, so you generate some bromine. So it's a side product. It's not very helpful because you wanted to add HBr across, which means some of your alkenes are going to be dihalogenated. Okay, we can do a radical bromide and a radical carbon to actually make a dibromo compound. So that's not very helpful either. Or we can have 2 of these radical couplings and make a much larger molecule. So all of our termination steps are actually kind of bad right here. But the fact that it adds that way is very interesting. So now we have our bromine here. Okay, in HBr, what was in HBr and an alkene just without the peroxide, which was the electrophile and which was the nucleophile? So the hydrogen, the partially positive hydrogen, was looking for electrons, and it found those electrons in the double bond. So it was attacking the double bond for its electrons. Here, what do we have? Our bromine is now the electrophile. It's looking for the double bond, but it doesn't need both electrons. It only needs 1. So it's now an electrophile. So our electrophile is still attacking the least substituted side. Okay, so now without it, the hydrogen adds on the more substituted carbon in the presence of our peroxide. So it's anti-Markovnikov. Seems that way, right? However, in Markovnikov's rule, the real rule, if you read his description of it, is the electrophile adds to the carbon with the most hydrogens. We've changed the role of bromine in our system. The hydrogen was the electrophile without peroxides. The bromine's the electrophile with peroxides. So really, it does follow Markovnikov's rule. But remember it as giving the anti-Markovnikov's product, but it is following Markovnikov's rule. Okay. So without the peroxide, though, you get the carbocation and you get rearrangements. Okay. So remember this little thing here? We did this. We made 3 different alcohols from the same compound. We did, let's see, hydroboration to get the primary. We did oxymercurization, demercurization to get the secondary. And when we did water and that, we rearranged and gave us a tertiary right here. Okay. So if we had just HBr with this compound here, it would add across the double bond, but it would rearrange doing a 1,2 hydride shift, giving us our tertiary alkyl halide. Okay. And if you want the tertiary alkyl halide, that's great. But if you don't want the tertiary alkyl halide and you don't want it to rearrange, add some peroxides, it changes the mechanism. Your bromine is going to add on the least substituted carbon, and then radical abstraction gets your hydrogen back. Your hydrogen abstraction gets your hydrogen back on your number 2 position. So it seems backwards, but it's a great, powerful tool to get to your primary alkyl halides. Okay. All right, so let's see. All right, and I think I want to stop here because I want, oh, I can do that. Okay, let's talk about the stereochemistry. I stopped here for the other class because we took longer to do that. The activity. So I'm just going to talk about the stereochemistry here. So if you're looking at your radical here, it's that, oh, okay, we're going to get racemization, aren't we? Just like in a carbocation, because you could attack from the top or the bottom, the incoming radical can form that bond at the top or that incoming bond at the bottom. And so what we're going to see, if it comes from one at the top, you're going to get R, comes from the bottom, you're going to get S. And there's no selectivity. So in the case of non-chiral alkanes, they are going to make racemic mixtures of enantiomers. Okay. If it generates a chiral center during that. Okay. If you have a chiral alkane undergoing substitution to form a racemic mixture, okay. So why would the chiral alkane also give a racemic mixture? Well, we're not attacking that chiral carbon, we're attacking, you know, a hydrogen or something next to it. So we're giving it forming that planar structure so it can come from the top or bottom, so you're going to get a mixture. Yeah. Okay. Alkenes undergo radical addition to form racemic mixtures of enantiomers as well. Okay. Because that radical that's formed, that secondary radical that formed, it's on that square planar with that p orbital, with their top gives you one isomer, bottom gives you the other isomer. So, but if your chiral center is not where the reaction is happening, you don't change that chiral center, you just add a new one. So there. So questions about stereochemistry. See why it's exactly the same as the stereochemistry with carbocations, E1, SN1 reactions. All right. Okay. So now we were talking about the carbocation stability, right? And we said it's the same for radicals here. And what we learned was that the allylic carbocation or the benzylic carbocations were actually more stable than tertiary carbocations. Okay, we see that true in our radicals as well. And it has everything to do with resonance. We can start with the radical on this side, but again, it can use one electron from the pi bond and leave one electron here. So it's constantly going back and forth between these two structures. So we only have a partial radical on each of these two carbons, making it more stable. It's not a full radical on there, it's just shared between those. And in the case of benzene, just like before, it can actually go and start moving that radical around the ring. So there's actually 5 different resonance contributors, so it's stabilized that benzylic radical. And so benzylic radicals can be, the best stable product. Okay, and we'll do more with that later. All right. So that means that when we reorder them, they're going to be analogous to those of carbocations, but we are making our primary radical, our vinyl radical, and our methyl radical. We can make them. They're not that hard to make. But our benzylic radical is most stable. Our allylic is about the same stability, and our tertiary radicals are the most stable. Okay. So the cool thing is, because they're more stable, they're formed faster, right? Because the barrier is less. And because they are formed faster, you get a greater yield. So that's really neat that you get these high rates of formation for both of these radicals, and they are done. Now, let's consider if you have them in a different part, where your different radicals are going to be. So in this case here, we have our radical is going to be going from a secondary to a tertiary, right? Because it goes back and forth, back and forth. So that means this is going to be a more likely resonance contributor because it's more stable. Okay. In the case here, we're going from a secondary, we're going to move it over here to a primary. But the secondary is the more stable and is the greater resonance contributor. Okay. So what you'll see is you should see more reaction take place on the tertiary in this one and the secondary in this one as your major product. It's faster and more stable. Okay, questions? Okay, I am definitely going to stop there for now so that I can make sure I don't get too far away on my own. All right. Thank you very much. We have quiz only on chapter 9 on Wednesday. We'll have chapter 10 the following week. Next week, or maybe this week, next week I'll be giving a bonus quiz. It's a take-home quiz. You get to draw me a lot of stuff and upload it by the following Monday. So,
What's it gonna be over like that?
it's going to be reactions that you get to draw out.
Okay.
So I'm using it as a bonus thing. You can use the book, just don't use anybody else. Don't use CHEM. They're wrong half the time anyway. But use the book and just draw out the reactions. And then and then everybody should probably get, you know, a 9 or a 10 on it if you use the book. So that would give you a good grade. All right. So that'll come out either this week or next week, but that's an extra one. So that's total of 12 quizzes, and I'm dropping the lowest 3. So fear not, it's getting better. Okay. Oops. All right. I'm going to stop sharing and I'm going to stop recording. And here are, all right. I'll see you guys later. Stop recording.